Morning, guys. So we've made it to the end of our waves optics section. What I was thinking of doing is just doing a quick summary of the major concepts and some of the major vocabulary, and also getting you to practice some more questions here. There was a little bit to do with sort of relativity and radioactivity as well. That also is going to be included on your test as well. So let's just start off here. We started off looking at the terminology, what is a wave and how did it differ from the types of kinematic motion that we had. The function of a wave is known as a disturbance. It's like a message. The whole point of this message here is to transfer energy. It's going to move energy from one place to another place. We started qualifying those waves here as different types. So your waves here can either be electromagnetic waves, so electromagnetic waves. Really, the only example that we had there was light. For electromagnetic wave here, these ones here don't require medium, so I'm just going to say they don't need a medium. They can actually travel through the nothingness of space. We saw that there were different forms of electromagnetic radiation again. A spectrum here just means a huge spread. Turns out the visible portion of our spread here is actually a really, really tiny portion. So our rainbows will always be in the order sort of Roy G. Biv. If you have colors, you can do that here. So Roy G. Biv. They're not all evenly spaced, by the way. Blue, violet. And we had, as we started looking at some of the terminology, we had actually looked at a couple things I can measure, one of which was called the wavelength. The red end is always roughly the 700 nanometer side, whereas the purple or the blue end is always referred to as the 400 nanometer side there. But that is actually just a really, really tiny fraction. There are forms of light here that are less energetic than visible. So we can go into the red region, so infrared radiation. We can have microwaves, again, not evenly spaced here, but at least I can have that relative ordering. On the other side here, similarly, I can have three other categories, not evenly spaced. I can go beyond the violet, so we get UV, ultraviolet. We can get X-rays, so at some point they actually didn't know what they were. That's why they call it, it's unknown, it's X. And we can actually get gamma radiation. When we look really deep into space, we can get pulsar stars actually giving off gamma radiation. We also use gamma radiation for chemotherapy, so you may have heard of that as well. Those are all forms of electromagnetic light. Things that are constant, however, so everything on the spectrum, all light waves travel at c, and c implies that it's actually traveling through nothingness, and this one here was 3.0 times 10 to the 8 meter per second. We saw that with relativity towards the end of this chapter here. We saw that things that move faster, their clocks slow down and their masses tend to increase. The speed of light actually represents some maximum speed that you can never reach. Things get really, really weird when we get close to that speed of light. However, these guys here are different. We already talked about wavelength here being different. We can actually measure, based on the way I ordered it here, we actually have increasing energy. As you go to the right hand side here, we're going to see energy is proportional to frequency. So this is going to be higher frequency. If I were on a metaphorical boat and I was bobbing up and down as the waves push me by, I'm actually going to go through many, many cycles in a given second, because this light wave here is traveling really, really quick capacity, and also because the wavelength itself is actually getting shorter or lower wavelength. So I'm going to rehash for you some of those formulas in a second here. We just want to rehash some of the terminology before we do that. So electromagnetic radiation is one type of wave. The other type of wave is referred to as a mechanical wave. There is also what's called a matter wave as well, but we don't need to worry about that. For a mechanical wave here, these ones here, they do require a medium. That's the key difference. So light can travel through medium, no problem, but they don't need it, whereas mechanical waves here definitely require medium. So we can categorize mechanical waves here also as two types. We can call mechanical waves here either transverse waves. I picture here a transverse waves here. If you look at the particles in the slinky, even though your wave may be going left and right, the particles themselves are actually perpendicular. So I think of the word perpendicular for transverse. For a longitudinal wave, also called a compressional wave, this time here, the wave motion still may be sort of straight across, but it's like taking a slinky, compressing it, and then as you let it go, it can sort of bob more kind of widely separated, not as widely separated here. In this case here, it's just parallel to the motion. So that sort of differentiates between what's a transverse wave and a longitudinal wave. Let's rehash some of the terms here, and then we can look at some of our formulas. Let's pretend we're taking a picture. So a y and x-axis, maybe of some water waves here. This is periodic motion because it sort of repeats, it oscillates over and over again. We call the tops of these waves here crests. We call the bottom troughs. We can label a couple different terms here. We can measure what's the distance before the wave repeats itself. We call that distance there, we call that the wavelength. Wavelength, we're going to use the Greek letter lambda for it. Sometimes they just say crest to crest distance. It's just easy to sort of see where the crests are. That's why it's nice to do. I can say trough to trough. I can say sort of this midpoint to this midpoint as well, as long as it's sort of the distance until the wave repeats itself. So instead of measuring the total distance that this wave actually travels, I'm just measuring the distance for a unit before it actually repeats. We have that there. We have when there was no wave, you can call it the rest line or the equilibrium line. We can actually measure the amplitude. Amplitude is always a positive number. Amplitude actually measures what's the maximum distance from the rest to the crest or from the rest to the trough. So this guy here is called amplitude. We can use capital A for that there. Amplitude there would be the maximum distance to the crest or to the trough as measured from the rest line. So that's fine. That was just taking a nice picture of the water wave here. What we did here is we then compared it against another graph. Coincidentally, this graph here ends up looking the same. If I was actually on a boat sitting out on the ocean, I start my clock here at 0 seconds. I'm sitting there, so I'm on the rest line. As time ticks forward, the wave itself is actually going to start pushing past me. And as it pushes past me, I'm going to travel up with the wave to the crest. The bottom part of the wave then pushes past me. In time, I'm just going to follow this wave here. I'm going to oscillate up and down. Sure, I might have the odd sort of front and back motion as well, but like a transverse wave, I just end up bobbing up and down as this wave zips past me. If I actually record that then, at time 0, I was basically on the rest line. The wave first pushed me upwards. I go up with the wave then goes downwards. I basically end up getting the same sinusoidal shape as previous. But this time, I can't take a picture of this because this one here is actually in an increment of time. A picture would need to be displacement. It's going to be a y-axis or an x-axis. In this case here, I'm actually just staring at my clock and I'm saying, okay, at 0 seconds, I'm this high. Oh, in maybe 5 seconds, I'm at the peak. Oh, in 10 seconds, maybe I'm back down here. I'm actually plotting where I am on this wave. Am I brought up with the wave or brought down with the wave here? This time, because it's an increment of time, sure, we can still have a cycle. Sure, we can still have the time it takes to get one full motion. But like I mentioned, this is now a time. Instead of calling this a wavelength, this time I'm going to call it a period. Period, we're going to use capital T for that there. This is now emphasizing here is the time for one cycle. We can do the reciprocal of that there, and we can say, well, if I don't want to give you an infinite amount of time, maybe I'm waiting many, many seconds for a whole cycle to pass by. What if I instead give you just 1 second? 1 second happens to be convenient for you here. Up to this point, I've just been using F. Careful, frequency is sometimes also using the Greek letter nu as well. So nu is like it's almost like a V with a little tail. That also means frequency. And this frequency actually just does the reciprocal of it. And it says, I'm not giving you infinite time, infinite seconds for one cycle. It's actually going to say, how many part cycles do you get per second? And that's actually going to be measured in a unit hertz, as we'll see in our formulas here. So this is the metaphorical, how many times do I rock up and down as this wave here pushes me by. With the water analogy here, not too bad. Even speed of sound, not too bad. Speed of sound is about 300 meters per second. But as you start looking at those electromagnetic radiations again, first thing, light is traveling at a ridiculously fast speed. The water wave is going to zip by you, and let alone the wavelengths are on the order of nanometers. We'll see that in the next example here. The distance between one peak and the next peak is actually very, very narrow, so I'm going to bob up and down. If you give me 1 whole second, I'm going to bob up and down millions and billions of times, and we can actually calculate how much it is. So first practice question here. Let's take a look at visible light, because we're sort of used to that. So just as an example, let's say I have a green laser pointer. When you design laser pointers here, you can actually play around with what gas actually is causing that stimulated emission, causing that radiation. So usually all laser pointers always give off the same wavelength. So one typical wavelength for a green laser pointer here is it gives off a wavelength of 532. That's the amount of energy that's carried. So again, it's important for you to keep in mind, it's not like the green laser pointer, it's not like the light photon itself is actually zigzagging back and forth. Light is just traveling in a straight line. But if you want to represent how much energy do these photons carry, do these little packets of energy carry, we can draw this metaphorical up and down. These would actually be oscillating electro and magnetic waves, if you go on to physics here. Wavelength here is the distance between one peak and the other peak here, and this wavelength here is a distance of 532. Nano means 10 to the negative 9, so times 10 to the negative 9. If you put this in your calculator, it'll probably spit out 5.32 times 10 to the negative 7. It didn't change anything. It did say nano was actually a 10 to the negative 9, so I've done that part correctly. It's just that I still have hundreds of nano. In proper scientific notation, if I just move the decimal place over, I actually only have 5 times 10 to the negative 7. So totally okay for you to type it in 532e negative 9 or type it in proper scientific notation. What I want you to do in this question here is see if you can calculate. We're given the wavelength. So I want you to calculate the frequency, calculate the period, and calculate the energy of this photon. So what is this energy as represented by this zigzagging back and forth? I'm going to just remind you of the formula so far. We have the universal wave equation. On your formula sheet, it may say V is equal to lambda f. Because we are specifically looking at light, we can actually put in the speed of light ourselves. So this is our constant, 3.0 times 10 to the 8. Assume that's in vacuum. We saw that even with refraction, when it entered into air actually didn't have much index as well. Pretty much the speed was still 3 times 10 to the 8. So we have wavelength there. We can find frequency, no problem. Frequency and periods are opposite of each other. So period is equal to 1 over frequency, also on your formula sheet here. So once you know the frequency, you just take the reciprocal of it. And lastly, to get energy, energy is given by the Planck equation. The energy carried is proportional to the frequency. The more times I bob up and down, the more energy I actually carry. So let's just try out these formulas here. You can always pause it and try it out for yourself as well. If I take 3 times 10 to the 8, if my wavelength here is, I'm going to type it in, 5.32 times 10 to the negative 7, what's my frequency? So let's calculate a frequency, make use of that EXP button. So 3e8 divided by 5.32e negative 7. This gives me a whopping frequency 5.6 times 10 to the 14. Frequency is measuring how many full cycles do I get in each second. So really, cycles isn't really a unit, right? I know the wave is going to repeat itself. Really, this should be 5.6 times 10 to the negative 4 for every second that I transfer over. And what we instead do is we define this as hertz. So we're actually going to say I actually travel 5.6 times 10 to the 14 full cycles, full up and down motions each second. Right? And that's given by 5.6 times 10 to the 14 hertz. Once you have frequency here, we can figure out, well, that now period sounds a little crazy now. If I'm bobbing up and down 10 to the 14 times every second, it's not going to take that much time for you to actually travel one cycle. So let's try it here. Period is equal to 1 over frequency. Let's take this 5.6 times 10 to the 14 number. If you can keep it unrounded and you calculate even better. I take 1 over that, I'm getting 1.8 times 10 to the negative 15. And that one is a time, that one is a second. As expected, 1 whole second. You bob up and down many, many times. If you just give me a fraction of a second, I would have bobbed up and down once. So that sort of detours you over to period. Frequency will also help you get to energy. So that's a nice hint here. See if you can do whatever you can to find frequency, because through Planck's equation, we can actually calculate the energy now. Energy is proportional. I'll give you Planck's constant if we need it. So this energy is equal to HF. Planck's constant is 6.63 times 10 to the negative 34. That's going to be joule second times it by this frequency, 5.6 times 10 to the 14. 6.63 e negative 34 times 5.6 e 14. And that gives us here 3.7 times 10 to the negative 19. Now, in general, when you actually do the sort of proper SI unit for charges and energies, we're not sort of that surprised with these numbers being so tiny, 10 to the negative a bunch here. But again, this is just for each photon. Imagine I have a green laser pointer and it's kind of sending in many, many photons. Each of the photons themselves carry this energy. It doesn't take many of them to actually stack up, let alone this light here is actually traveling very quickly as well. So make sure you're comfortable with some of that vocabulary there. In your projects, you applied it to musical instruments here. Frequency, in the musical case here, this will give you the pitch. This will give you sort of which note the sound is giving you. In the light example, this is giving us the color, or is giving us the wavelength. Amplitude is the other one. That's a sort of a measure of energy. Amplitude, the distance from the rest line to the top or to the bottom. In the sound case here, this actually gives us volume. And in the light case here, this gives us actually brightness. It gives us sort of the intensity. Depending on your application, you see that sort of it works its way out differently. So that's just a nice review of some of the terminology we've seen in the waves chapter here. Let's skip ahead and let's look into your optics section in a little more detail. In our optics section here, we had two keywords. One was the word here, reflection. The typical optical device here was a mirror. Yes, you can actually make like a half silvered mirror, so it's kind of acts as a mirror, kind of acts as a lens, but we're just going to go straight mirror here. I think of bouncing off, so that's reflection. The other way here is refraction. The main optical device there was actually a lens. All right, so we have this one here. In fact, in both cases, we actually do end up using what's called Snell's law. So Snell's law, also on your formula sheet here, n1 sine theta 1 equals n2 sine theta 2. It just becomes a little bit more important in the refraction case because we would expect going from one medium and entering into another medium. Earlier I had an n1, later on I have n2. In the reflection case here, because the mirror is nice and shiny and nice and flat, this time a light ray comes in, it's going to actually bounce back the way it came. You notice I actually end up in the same n. In that case there, if the n's are equal, they cancel out. If I inverse sine both of them, in this case here, it actually tells me the theta 1 is equal to theta 2. Let me actually rewrite these names for you here. We call this incoming ray here the incident ray, because that's oncoming. The one that after it bounced off, we can call that here the reflected ray, the bouncing off ray. And then in terms of the angles here, we can call this sort of the incident angle, because this is the angle that it comes in at. We can call this the reflected angle, or sometimes they even call it angle of reflection. Because we are staying in the same medium, there's a law of reflection that says theta I, theta 1, is equal to theta 2. And that's actually derived from Snell's law. So in this section here, we actually introduce this concept of n. N is called the refractive index. Refractive index. N. And basically here, this one I think of it as like an optical density. Density usually means how packed a material is, how stuffed in something is. In this case here, there are materials that are so packed in that actually makes it hard for light actually to travel through. So the higher the n, the harder it is to travel through. Some common ones that you have on your formula sheet, n for air is 1.003. N for water we use a bunch, 1.33 like that. In fact, the higher the number, the harder it is to actually travel through. When we actually think of a formula like the velocity of light is always frequency times the wavelength, we have to remember velocity is going to depend on this optical density. The velocity speed depends on the medium. If the medium is hard to travel through, light has to slow down. And depending on the marching band here, as it slows down, if one side slows down faster than another, that's what ended up causing the bending, as we saw in our lessons. The velocity depends on the medium. The frequency, however, just depends on the source. So whatever your laser pointer is, regardless if this marching band here enters, slows down, and bends towards the normal, the beat that's set behind here, we call these ones here wave fronts. And usually the wave fronts are measured the crests of the waves. So if I looked at the side on, I looked at all the sort of up and down motions here, I would just mark a bright band for every top there, and that's what the band I'm seeing for the wave fronts. So that's your optical density here. Let's practice a quick Snell's law question. Again, just for simplicity, I just imagine that it's like there's a laser beam that's kind of pointing out of your eye here. The optical density never gets to be overly high. Let's say I go from n equals 1, like air. I think diamond has something like n equals 1.5 or so, assuming that doesn't reflect off of it. I'm going to send in this light ray here, say at 25 degrees, and I want to know what the refraction angle is going to be. I know my brain's going to play tricks on us here. If we see a light ray actually coming at this angle, our brain actually interprets it as having come from a straight line. That's why we always interpret there's actually a virtual image. There's no real fish, there's no real light ray here. In reality, the light ray had actually bent, and I'm interested in finding this angle here. Be careful when you measure angles. It's always relative to the normal. It's always relative to the 0 degree, the perpendicular. Sometimes they try to trick you and they try to be like, oh, what if I told you this angle here is 65 degrees? You just do 90 minus that. Figure out the complementary, figure out the angle with the normal, and use that angle for your calculation. In general, when we go from a relatively easy medium to a relatively hard medium, we're going to bend towards the normal. We're going to get closer to the perpendicular. So let's just try it out here. You can practice Snell's law here. Hopefully not too bad. M1 sine theta 1 is equal to N2 sine theta 2. N1 was a 1. I sine 25 degrees. N2 is 1.5. It's a harder medium. What's the new refraction angle here? So let's take sine 25 divided by 1.5. This gives me here 0.282. Keep the whole number in your calculator. I need to do the inverse sine to get that answer. Arc sine of 0.282 gives me the angle of 16 degrees. So therefore, relative to that same normal, that perpendicular, I'm going to leave at 16 degrees. And there we go. We see that it's actually bent towards the normal. We will not get any critical angle in this case here, going from easy to hard, because you can bend as close to the normal as you want. There's no limit. However, on that note here of critical angle, let's reverse it. Let's say we actually were in the medium that was n is 1.5, and let's say we wanted to go back out into, let's do another medium, let's do 1.20. So not necessarily air. Again, I'm going to pretend I'm Cyclops here. I'm going to pretend I'm going to send in a light ray. I'm going to send in a big angle. I'm going to assume that this big angle doesn't get out. So let's say I send it in at 80 degrees. I want to know what my refraction angle is. I want to know what angle does it leave at. Let's try out Snell's law. So N1 sine theta 1, N2 sine theta 2. I'm starting off in the 1.5. I'm sending an angle of 80 degrees relative to normal. My N is 1.2. What's the new angle that it's supposed to get out at? 1.5 sine of 80 divided by 1.2. This gives me here 1.23. Sine of theta 2 is going to complain. If you try to inverse sine this one, your calculator will just give you an error. It's saying because we're going from a relatively hard medium to a relatively easy medium, I'm expecting to bend away from the normal. And in fact here, because I'm looking at such an intense angle, I bent so far away from the normal. Here's the normal. I'm going to bend at a bigger angle. I bent so far away, the maximum ray that I can actually leave would be 90 degrees. That's called your critical angle. But this is so far beyond that I bend back into the solution. Again, you'll see this the next time you're at the bottom of a swimming pool. You'd expect water to be totally clear. You look up, you can see the roof. For some distance here, you can see outwards. But at some point here, you start seeing the shimmery of the water surface. In fact, that shimmery is actually just a reflection. It actually bent so far back that it's actually back into the ocean itself, or pool itself. And because it is reflection, we get a concept here called total internal reflection. Total meaning all of the light, none of it actually gets out. Internal means it stays in the medium, and we actually get, reflection, because reflection here is actually bouncing back. In fact, people who design fiber optic cables would do something like this. So fiber optics here is like a glass cable. We just make sure when we send in our first ray, relative to its normal, we want it to be bigger than the critical angle, so that ray then ends up bouncing backwards. If you do the sort of angle relationship here, every time I hit a normal, I'm always going to be beyond that critical angle. I can send a light signal down this fiber optic cable pretty easily. How do I not confuse the sort of different channels and different signals of light here? I can play around with which angle I actually send it in at, what the wavelength I send it in at. It's still going to totally internally reflect. It's still going to be stuck in this fiber optic cable, but you see that I can actually send multiple messages through the same fiber optic cable. So in this contrast here, they might ask you find the critical angle. So find out what was that maximum angle that just managed to get out. Find the critical angle. I'm going to make a note here. This will only be going from a hard to an easy medium, from a high end to a low end, because that's when I bend away from the normal. And all you're going to do is you're going to go N1 sine theta 1 is supposed to be N2 sine theta 2. This time I knew the ends. I started off from medium 1.5. I don't know what the critical angle is. I don't know how big the angle I can look out at, so that's theta c. The n on the other side is 1.2, and I want this ray here to just make it out relative to normal is 90 degrees. Sine 90 happens to be 1, so that term just drops out. And then we actually just want here sine theta c, double check my numbers, theta c, this won't complain anymore. Theta sine, inverse sine of 0.8 gives you here 53 degrees. So in fact, 53 degrees, if I look out at 53, that was the last ray that would have gotten out. It just manages to peek out, just manages to get out. If I even look at it at 53.1 or 54 degrees, even at 54, let alone my 80 here, would definitely just reflect back the way it came. So make sure you do get some practice with Snell's law there. As you start looking at mirrors in a little more detail, we started doing those ray diagrams. Make sure for a ray diagram you actually use a ruler, measure the focal length, center of curvature, things like that. Let's look at our mirrors here and introducing some of the language again. For a plane mirror, for a flat mirror, remember here you are called the object. This could be a candle that's actually emanating light here. I can measure how tall you are as the height of the object. I can measure your distance to the mirror as the distance of the object, dO. Distance to the mirror is always going to be positive. Because a mirror is reflective, I'd expect the real side to be on your side, and the virtual side will be behind the mirror. Remember what I mean is not, actually walk up to the mirror and actually physically look, turn around behind the mirror. What I'm saying is you're actually looking at the shininess of the mirror surface. It's like there's a virtual world inside. It's like you're actually inside the picture. When we actually track a light ray that actually comes to us straight across, our brain interprets it as if it has come from behind. So our brain actually plays tricks on us. No real light rays actually get into this, so it forms a virtual image. Nicely for a plane mirror, the DO is equal to the DI, and then the HO is also equal to the HI. So there's no distortion. As you walk up closer to the shininess of the mirror, it's like the image also gets closer to you. This right here was a little more interesting when we started looking at curved mirrors. For curved mirrors here, I want you to pay attention to the just the two main keywords. One is a keyword here of a converging mirror, and the other is a keyword of a diverging mirror. Those two words here by themselves, converge means comes together, right? They get closer, whereas diverge means they separate. We're going to see when we do a focal length here, the focal length is actually positive. So in terms of mirrors, the one that actually converged was actually a concave shaped mirror. It's like looking at the opening of a cave. So in this case here, I'm going to have a cave. So far, we've just been doing curves that were basically circular. That way we can label the term. If this were really a circle, it's really distorted here. But if there really was a circle, we can have the center of the circle called the center of curvature. The focal length will always be half the center of curvature. We can have the vertex, which is where the mirror actually intersects with the principal axis. Principal axis is just sort of where I measure from. Remember, for a ray diagram here, we just drew two rays. We figured out what happens to those two rays. Wherever those rays intersected, whether they're on your side or whether they're on the far side, we were actually able to make a prediction on whether the image was virtual, magnified, whatnot. So let's imagine we actually stand out here. For a concave mirror, your image is actually going to depend on how far you are. Our two rays here, I'm just going to remind you here, a parallel ray converges through F, and a ray through C they use the language of undeviated. It means unchanged. So let's draw these two rays here with the ruler. A parallel ray with the principal axis, because this is a converging mirror. The light ray bounces off the shininess of the surface. It can't get through this mirror. It ends up bouncing back this way. And then the one that goes through the center curvature, this one here is going to hit the normal straight on, 0 degrees on, 0 degrees off. It's just going to come straight back. Where these rays here intersect is actually where your image is. Because for a mirror, this is the real side. The real side is positive. The virtual side is here. Because the intersection here is on the real side, we can actually project this on a screen. There actually are light rays that pass through this. Our image will actually be some language we can use here is we can say inverted. It's upside down. Based on if I actually did this with a ruler, you might be able to conclude that this is diminished. It's actually smaller than it was. Because it's real, we can actually project it onto a screen. If you put a piece of paper right here, you'll get a really nice clear image, a nice reflection of what the candle was, what the object was there. If I'm even a little bit too far off, a little bit too close, a little bit too tight, the rays here have not converged yet. I'm just going to get a slightly blurry image. We might get a slight look at what the image is, but until it's actually exactly at this DI, this distance of the image, it won't be clear. This one here, you can try out your ray diagrams. Your image depends on your D naught. As you steadily walk closer and closer to the mirror, you get to see the image is different. Case in point here is if you walk right up close to the mirror, and next time you look at the inside of a spoon, you actually see a blown up picture of your eye because it's actually a virtual image and it's much larger, magnified, upright image. You don't need to memorize that. You just draw the ray diagram, or like we'll see using our thin lens equation, we can actually calculate for that. How about for a diverging mirror here? For a mirror, we're looking at the convex mirror. We're looking at the bulgy side. So again, we can label our axes here. This time, because the shininess of the mirror is here, the curvature is sort of against you. This time, the center of curvature by itself is actually a negative number. The focal point is also a negative number. In this case here, we're always going to be here. This time, no matter how far I am from the bulgy side of the spoon, I'm going to actually figure out my virtual image is actually going to be tinier. You can draw your two rays again. Parallel ray reflects as if from the negative focal point. I know the light ray here never actually makes it through. A parallel ray to the principal axis, it was supposed to just bounce off. It's going to bounce off as if it had come through F. Sort of that's a nice corollary with the other side. Parallel would have converged to the focal point. The other one that's undeviated here is, again, a ray through C. This one here hits the center curvature head on, is undeviated. This one here is unchanged. So again, using a ruler, if you can just, real light ray here strikes the mirror, it's aiming towards center curvature, it never actually makes it through, but it's equally well going to hit 0 degrees on, 0 degrees off. It's going to bounce off this way. You'll notice this is why we call it diverging, because these light rays are never going to intersect. Again, our brain plays tricks on us a little bit here. Wherever the light rays converge actually creates an image. This is on the virtual side, so we call it a virtual image. It's now a smaller picture, it's a little bit diminished, and it's still upright. You can't put a piece of paper here into the mirror itself, so therefore it's a virtual image. It's just our brain playing tricks on us. You're going to find in parking lots and convenience stores, they put mirrors that are curved convex so that they can actually image more of their store at any given time. Let's have a look at lenses before we do our equation then. For lenses, in a very similar fashion, we can have the language of which one is converging and which one is diverging. So for a lens here, so curved lenses. Again, we're going to use the terminology here. Converge means it comes together, or diverge means it separates. This time, because for a curved lens, I expect the light rays to actually get through, with the exception of the object distance, which is always positive. Let's say I'm standing here. I'm going to have an object distance. Right, that's how far I am away from the lens. This one here is always positive. Right. I would have expected that the light rays, they're supposed to hit the lens and they're supposed to be able to actually go through. So what I would say is I would say the real side, positive side, should actually be on the far side, and the virtual side should actually be the side that I'm on. Again, just treat that as an exception. Object distance, the DO is always positive. Again, you can look at your ray diagrams here. We're going to draw two rays just for convenience. We can have a focal, we can have a 2F, we can have a focal on the other side and a 2F here. What we're going to have here is, again, parallel ray converges through, let's say, the opposite F, the F on the real side. So there's my parallel ray, it goes through F. The ray that's undeviated is actually the one that goes through the vertex. It goes through the center point. So a ray through V is undeviated. It's unchanged. So in that case there, if I send a light ray just straight head on, I should use a ruler here, straight head on, and if it cuts through the vertex, this one here will just cut straight through. If I did this more properly here, I can actually see, well, they're going to intersect somewhere out here. I know it's going to be an upside down image. Whether it's bigger or smaller, I'd actually have to measure rulers, make sure the center curvature is actually double to actually figure out where that is. Lots of simulations on the resources page, so you can play around with that. Nothing you need to memorize, but our formulas will then tell us what this is. This one here, in a similar fashion, it's always the converging ones here This one here depends on d naught. Your image is going to change, it's going to move around depending on how close you are to the actual lens itself. For the thin lens, for this mirror, you can do a double-headed arrow going up and down this way. Realistically, it's actually bending twice, bending once as it enters the mirror, as it enters the lens, bending again, but we're just going to assume that it just bends once and for all at the vertex line. For diverging, what we want here is actually a biconcave lens. Again, we're going to use a notation. We're going to assume that it only intersects and actually bends once. We again only have a focal and a 2F, a focal, a 2F, and a vertex here. Your ray diagram here, a parallel ray separates as if from the virtual focus. As you get more practice with this, you can pretty much easily memorize what the ray diagrams look like. But what I'm saying here for that ray, it goes in parallel, and it's going to leave as if it had come through F. So I need to make my writing look better. From virtual focus. And the reason why I call it a virtual focus, that's going to be the negative focus. That's because I expect light rays are supposed to get through. This would actually be the negative side of the lens. So virtual focus, sometimes out of the math that negative comes, so I know what type of lens it is. In the other case here, you might need to put in the negative if you know it's diverging. So 2, the other ray here is also undeviated. This is the one that goes head on. We definitely see that it's never going to converge on this side, but it is going to always converge on this side. It's on the virtual side, so you can't put up a screen. Even though there is one real light ray, the other light ray here is dotted, the other one here is virtual, so this one here is definitely a virtual image. So as you sketch your ray diagram, depending on where they intersect, you can actually qualify whether it's real, virtual, and whatnot. So in this case here, a ray through V is undeviated. Right. And that one, there is actually a real light ray, but again, because one of them was a sort of dashed line here, that one here is actually not a real light. So let's just switch over to take a look at our equation. This thin lens equation works for both mirrors and lenses. So we had 2 equations. One was 1 over F is 1 over di plus 1 over dou. The other one was magnification is high over ho equals negative di over dou. Right? So this gives us some nice relationships between distance, object, image distance. A couple things to remind you. Again, the focal length. It is positive whenever we deal with things that are converging. So this is going to be a concave mirror or a convex lens. It is going to be negative if it's diverging. You might need to include that yourself, or if it comes out that way, that's what happens. M in general is called the magnification. It tells me whether it's going to be bigger or tinier. Magnification will be just this ratio here. It's going to be between 0 and 1. Between 0 and 1, we can say the image is diminished. It's now smaller. Anything bigger than 1, it's now going to be magnified. It's now going to be larger. It is possible that out of the math actually comes a magnification that's actually negative. If this magnification here is negative, it means inverted. If this one here stays positive, it means it's upright. It's standing with the same orientation as it had before. So let me just let you try this out here. Maybe 2 questions for you. A 5 centimeter tall object or candle is placed 3 centimeters away from a convex mirror. The image is upright and 1 centimeter tall. All right, so the image of the candle is upright. It's still the same orientation, but it's a little bit smaller. Question for you here is calculate. Ooh. Sorry, my writing is looking so scratchy. Calculate the focal length. So calculate the F. How far is that? Calculate the magnification. That one should be an easy one because I already have the heights there. And calculate the image distance. Okay. So I would recommend pausing the video, trying it out for yourself. What I would do here is I would just start with formulas. 1 over F is 1 over di plus 1 over dou. We have M is equal to high ho, negative di over dou. Let's label these terms here. A 5 centimeter tall candle, that's going to be the height of the object. is placed 3 centimeters away. This is the object, so this is going to be the DO. That's going to be a positive distance. It's away from a convex mirror. A convex mirror is the one that bulges out at you. In this case here, we would expect to actually have a negative focus. So if, right, this is the diverging one, if they give me, oh, with focal length 5 centimeters, I put -5 because I know it's negative. In this case here, because I'm asked to actually calculate the focal length, I just would expect out of the math comes an F that's negative. The image is upright, so magnification here is going to be positive. We know it's 1 centimeter tall, so that's going to be the height of the image, and that's all we basically need. So let's try it out here. The magnification here is going to be high over Ho. High is the 1 centimeter divided by the Ho, which is 5 centimeters. So therefore, right away, magnification is 0.2. Right? This one here is upright, it's positive, and it's also smaller, so it's diminished. This one here is going to be equal to negative di over do, and we knew that the do was actually 3 centimeters. So let's actually plug in 3 centimeters here, and this equation actually gives us the di is actually going to be negative 0.6 centimeters. I'm doing everything in centimeters because everything is just set up as a ratio. So there we go. We got the image distance, we got the magnification. Once you have the di, you can plug it into this final equation. 1 over f is equal to 1 over di, negative 0.6, plus 1 over do. Do is equal to 3 centimeters. Careful, it's still reciprocal on this left-hand side here. So 1 over negative 0.6 plus 1 over 3. This gives me negative 1.33. No problem switching over to decimals. It's a little bit easier than doing fractions. And the focal length, as expected, is 0.75 centimeters. It's negative because it was virtual. I'm just going to leave you with another question just for you to practice here. An object is magnified by 2 and upside down. Find the relationship. It's just a ratio this time. Find the relationship between di and d naught. Find the sign of f for the lens and identify the curvature. So this equation here works both for mirrors and lenses. All I'm qualifying for you here is we are looking at a lens. Identifying the curvature just means, is this a concave lens or is this a convex lens? Try it out for yourself. It's a little bit lacking in numbers, but you should be able to do that derivation. Maybe drawing a ray diagram will help you in finding that as well. Lastly here, we did this small section on special relativity and radioactivity. The most important thing from special relativity are those postulates. So what are the things that Einstein assumed for special relativity? The 2 postulates were, first, a relativity principle. When we start traveling at relativistic speeds here, there is no preferred inertial reference frame. All the physical laws stay the same. Physics stays the same. Again, the whole notion here, when they say special relativity as opposed to general relativity, they're going to use this term here, inertial. And inertial basically means there is no acceleration. They're really easy to use the term reference frame. Reference frame just basically means point of view. It's like who you ask. Remember, it means both people are correct, and yet things that we thought were constant, like time, like mass, and in fact, in this weird special relativity case here, we actually see what's constant is actually the constancy of light. So constancy principle or constantly postulate, and it basically says no matter what you're doing, the speed of light is always constant. Doesn't matter if there's any relative motion, time will actually slow down to make sure that's guaranteed. So throughout this section here, whenever they need speed of light, you can just use our constant 3.0 times 10 to the 8. We saw in our lessons here, this sort of represented a maximum speed in our universe. When we get close to speed of light or travel around relative to the speed of light here, 3 conclusions here is we have time dilates, time slows down. We have the mass increases, things get much more large, That's why it's more hard to accelerate even a little bit faster than that. And we also have length contraction. Again, in this section here, it's very easy to get mixed up. Is this a space-time? Is this relative to the ground observer? Whatnot? Just keep those three constants in mind. Make sure time is slowing down, make sure mass increases, and make sure length contracts. I think I did get the time formula correct on your formula sheet. So T naught is equal to T, 1 minus V squared over C squared. I did want you to make a correction for the L naught one. L naught should read L is equal to 1 minus V squared over C squared. And as well, the M naught one, M should actually be 1 over 1 minus V squared over C squared. This guy here is called the relativistic factor. We call that gamma. So this is the relativistic factor. And just based on the way I worded this here, these are all the moving observer. These are all according to the space person. So moving observer, this person here is the Earth observer. It's the person that looks like they're at rest. So this is the ground observer. Again, just some confusing terminology here. You could actually say, wait, the moving observer is actually in the spaceship. He's at rest relative to moving. That's why it gets a little bit complicated. But make sure when you punch into these formulas, make sure you do end up getting, again, time slowing down, mass increasing, length contracting. We also saw because the speed of light here has to be constant, we had the relativistic addition of velocities as well. The v total is equal to u plus v, 1 plus uv over c squared. What all these formulas basically say is when v is tiny, this term basically drops out, while time is basically, it's the same for both people. Length is the same, mass is the same. Or even this one here. When these u's here are very tiny here, the speeds here just add like you would normally. It's only when v gets close to speed of light, this relativistic factor here, this term starts mattering, and this term starts setting up a ratio, some fraction, to actually slow down time, to actually contract length, and actually increase the mass. So I'm just going to just leave you with a couple quick questions just for you to practice. This right here shouldn't be all that bad. I want you to do relativistic addition. An observer moving at 0.6 the speed of light throws an object at 0.4 speed of light. I want you to calculate the total velocity. If it wasn't for relativity, we'd just say, oh, the observer was already going 0.6, and now he throws an additional 0.4 relative to him. Well, just add those two. Well, he just threw it at the speed of light. We're going to use that relativistic formula here to actually figure out what it is. In terms of a sort of relativity argument here, in terms of half-life, I'm going to give you an element here, Seaborgium. Actually, interesting element. This one was actually named while the scientist was still alive. A lot of the elements were named after the fact. Seaborgium 266, that's its mass number. That's the isotope that I'm looking at. Seaborgium 266 has a half-life of 30 days. Oh, sorry, 30 seconds. Just wondering why that looked a little bit weird. 30 seconds. If sped to 0.95 the speed of light, how long Earth time would it last? And calculate the increased mass. Okay, so use the time dilation formula, use the mass increase formula as well. And then I'll also leave you with one last, one to practice with logarithms. So let's say I have cobalt 60. Cobalt 60 decays from 50 grams to 10 grams in 12.2 years. Calculate the half-life. In that case there, you'll need to use a formula here. Nt is equal to n naught. I will give you all these formulas. I just want to more so make sure you're comfortable using this here and see if you can calculate the half-life, which would be this constant k here. So keep practicing through those, practice your worksheets, and let me know if you have any questions. Thanks, guys. Take care.